Funziona.
All right, welcome all to this seminar. In this seminar, Alessio is going to present Data Arrays Freedom a la Mode, which is a seminar based on an article of the same name. I know nothing about this, so I have nothing to say. Welcome to the stage, Alessio.
Okay, thank you for having me again. We're talking about OCaml. So the problem this paper deals with is that we have in OCaml 5 we have finally support for multi-core programs, so we can have multiple OCaml threads running different code simultaneously on different cores. And with that comes, so we give great power comes great responsibility. We now have the possibility to introduce data arrays in the code. And the OCaml language doesn't provide any way to prevent or identify statically the possibility of data arrays, which is a common problem in pretty much all multi-threaded programming languages, with the exception of Rust and a few others. Having technical problems. Okay. So the goal with this paper is to extend the type system of OCaml to avoid this kind of issues. Or just to recap, the definition of data races we have here is that a data race happens when two different threads try to access the same memory location at the same time. At least one of the two accesses is a write, and the accesses are not atomic operations. So we are trying to prevent statically, by an extension of the type system, this kind of data race. And also we want it to be a backward compatible extension, so all existing OCaml code should compile and run the same as before, provided it was sequential code. Of course, we do not want to support the compilation of existing multi-threaded code because it could have data races. And also we want to be able to design and implement data structures which have internal aliasing and can be accessed by different threads and can be mutated by different threads. So you can imagine a graph or a linked list which is easy to do in sequential code, but also in programming languages such as Rust that prevent data races statically is notoriously a pain point. So the approach followed by this paper is to extend the type system with modes, which change the interpretation of a type. This idea comes from some previous work, Oxidizing in OCaml with modal memory management, which had the goal to improve the performance of the language by identifying values that can be allocated on the stack instead of on the heap, and then reusing memory locations. So this was actually implemented in the fork of the OCaml compiler from JStreet. And so this paper bases, this extension of the type system is based on this work with the idea that it can be implemented in this same fork, and then maybe in the future in the proper OCaml compiler. So modes basically can be applied to bindings, so let's, and the function types, and they change in some way how we see the type and the value associated with the type. There are basically 5 axes for each mode. So a mode is a quintuple of locality, affinity, uniqueness, portability, and contention. Each of these 5 axes is independent from the others, except in some ways we will see next. And also there is a submode relation between the modes. So for example, a global the global mode is a submode of local. This is basically subtyping, but at the level of modes. So I'm sure this is not clear at all, but we'll see every mode in detail next. So we start with locality. Basically, locality tells us whether a value is allocated on the stack or on the heap. So a global value as a permanent lifetime is allocated on the heap and is garbage collected. A local value is instead allocated on the stack. It has a lifetime which is restricted to a specific region. Locality also tells us if we specify that a function argument is a local. It tells us that this argument cannot escape the scope of the function, because this function, from what the function knows, this argument t could have a lifetime which is restricted to the body of this function. So the function is not allowed to return it or to save it in a global reference because it could be deallocated after the function ends. So here, the local parameter, we are trying to assign it to this global reference, and this is an error because this will let x escape its lifetime. But also, if we try to assign to the same global reference a closure which captures x, then we get the same error. The same error because this closure can be used after the call to f ends, can be used to get a reference to x, which is a local, so we cannot allow this to happen because it will escape its lifetime again. Global is a submode of local because we can always see a value with a persistent lifetime as having a shorter lifetime. This is sound, the value will be valid in the word restricted lifetime. Then the second mode is uniqueness. Uniqueness tells us if a value has been copied in the past. So unique values have never been copied. Aliased values could have been copied. Of course, we can always pretend that a value has been copied in the past. So actually, unique values can be seen as aliased, and this is what we have a submode relation. Here we have a function delete, which expects a unique parameter, and then we try to apply it twice to the same value. X starts off as unique, but then to apply it twice, it means that we have copied it. So by the time we try to apply this first delete, X is actually aliased, and so we get an error. The dual of uniqueness is affinity. So affinity tells us if we are allowed to make a copy of the value in the future. So a many value can be copied. Once value cannot be copied, so cannot be used once. This is a very simple example. X is once, so we try to add it to itself, and this gives an error. So basically, affinity and uniqueness are like the two faces of a linear type system. There is an interesting interaction between these two modes in the context of closures. So when a closure captures a value, the affinity of the closure depends on the uniqueness of the value that is captured. So a closure that captures a unique value can only be once, because every time the closure is applied, it gets a copy of its environment, and so by the second call, the value that was unique in the first call has become aliased. We cannot track the number of calls that a given closure is has been the number of times a given closure has been applied, and so we need to assume that we are in the second call or the third or so on all the time. And so unique, like a closure that can be called multiple times can only capture variables as aliased, and this will be important later. Here, for example, this function f, this closure is capturing a unique value X. Delete expects it to be unique, so this cannot be weakened to aliased. And so the whole closure must be once. Iter expects to be able to call the function any number of times, because it needs to call it a number of times that is equal to the length of the list. Instead, we are passing a once function, so this is an error, and this doesn't compile. Okay, so those three modes were actually the ones introduced in oxidizing OCaml. Now we have two modes that are specifically meant to deal with data races, contention and portability. Again, they are one dual of the other, as their affinity and uniqueness. Contention tells us if we are allowed to modify mutable fields in a value, and in particular if we are allowed to modify the contents of a reference. So a contended reference cannot be modified and cannot be read. A shell reference can only be read, and an uncontended reference can be read and written too. So here we have a function f that takes as input a contended reference, tries to assign a value to that reference, and this is an error. The name contention comes from the intuitive idea that when we share a reference, that reference becomes contended because multiple threads have access to it. And we don't want a mutable reference to be mutated by different threads, because that leads to data races. So we are binding these two packs, having shared the reference and having the ability to modify it. So we can see contention as telling us if a value has been shared in the past. But it's not exactly this, because this will be very restrictive. But as a first approximation, we can take this definition. Portability, so is the dual. It tells us if we are allowed to share the value in the future instead of in the past. So a portable value can be transmitted to other threads, non-portable value cannot. And this comes in the typing rules is basically used only once in the thread.create function. So we can, the way we spawn a thread in OCaml is that we pass a closure to thread.create, and this closure will be executed in a new thread. And we require that the closure is portable to do this. So if we have an unportable closure, this is an error. And there is an important interaction between contention and portability. A closure that captures an uncontended or shared value becomes non-portable. So if a function is portable, it means that it sees its environment as contended. So a portable function cannot access mutable fields in its environment. Portable functions are entirely isolated from mutable variables, and so they are safe to spawn in other threads. We have here a function f that is non-portable because it tries to read from this variable x in its environment, and so we cannot use it to spawn another thread. So this basically gives us a sharing XOR mutability restriction. You may know of the aliasing XOR mutability from Rust, where a mutable reference cannot be aliased, and an aliased reference cannot be mutable. Here we are not so restrictive because we want compatibility with existing sequential code, and existing sequential OCaml code relies on aliasing mutable references. But here we are just restricting what happens if we're trying to share references between threads. So a reference that is shared cannot be read or written to. And clearly, this is not very useful. It surely prevents data races, but it also at the cost of having the ability to communicate between threads. So in not a very helpful way, but we will relax this restriction later. For now, we take a step back. We wanted to keep typing all the OCaml code, that doesn't contain mode annotations. So we do that with the default mode, called the legacy mode, at which all the sequential code compiles just fine. So we assume that if we don't specify a mode, values are global, so garbage collected, can be used any number of times. We don't track their uniqueness. They are uncontended, so they can be modified. And most importantly, they are non-portable because we don't want them to work in concurrent programs because legacy OCaml code doesn't prevent data races. One final detail about the modes. We saw that they can only be applied in specific places, so in bindings and function types. So by default, they apply in depth to tuples, structs, and so on. So for example, in this function, f, which takes two values and returns them as a pair, if the first value is aliased, the second value is unique, then we need to choose a single mode for the return type. Here we can choose either unique or aliased. The only valid option is aliased because the unique value can be seen as aliased, but an aliased value cannot be seen as unique by the submodal relation. So aliased is the only choice, and this is a valid type, but it's not very precise because we lose the information about the second component being unique. So we solve this by introducing modalities. Modalities can instead be applied anywhere. They are basically wrapper types, so just normal types that change the interpretation of a specific mode for their inner content. So the solution here is to mark the whole pair as unique, but then say that actually the first pair is aliased. This has a couple of disadvantages. One is that we need to introduce and eliminate the modality explicitly using this box constructor and then the unbox destructor. And so this clutters the code a bit. And the other disadvantage is that not all modes give rise to a modality. And this is the reason why they are different concepts. Because if we allowed every mode to be a modality, then we would find that some combinations are not sound. For example, it makes no sense to have a local value inside a global tuple, for example, because the lifetime of a composite value is limited by the lifetime of its components. So if a component is local, then the struct or the pair must also be local. And this holds for other choices of modes. So we are a bit restricted on the front. But having modalities is still more flexible than not having them. So to recap, we now have 5 modes. From contention and portability, we get the sharing axon mutability discipline. And from locality affinity and uniqueness, we do get the performance optimizations from optimizing oxidizing OCaml. But actually, in the context of data races, we are not actually using them. So there is a reason if they are in this paper, and the reason is that, as we already mentioned, sharing mutability is too restrictive for us. We want actually to have communication between threads in a controlled way, of course. And so we will use the 3 modes to design an API that works around the limitations of contention and portability in a safe way. The idea is the same as in Rust. You have the core type system, which is safe but also restrictive, and then you have some APIs that are implemented with unsafe by circumventing the protection of the type system. But then you are confident that the APIs are implemented in a correct way and they expose a safe interface to the code. So the capsule API is this first API we are seeing for this purpose. The idea is that we can have complex data structures which have mutable references, which are also aliased, and we can encapsulate them in these capsules. The capsules make sure that only one thread at a time can access the content with the right permission. So we cannot have data races from two threads trying to write to the contents of the capsule. And also, it allows multiple threads to read at the same time. And this is done by tracking ownership of the contents of the capsule statically using some access tokens, which we call keys. And for that, we use the uniqueness mode. So a key can be unique or aliased. A unique key grants full access to the capsule, so read and write. An alias key instead just read access, because it represents shared ownership of the capsule. The API is made of two modules, key and data. The key module is this access token that we're talking about. So a key exists basically only at compile time. At runtime is just a unit. At compile time, we need to guarantee that different keys are treated differently by the type system. So we do that with an existential type. The idea is that this is the type of the key, KT, and this K variable is different every time we create a new capsule. So every time we create a new key, we get a different value of this type variable. This is the way we do it in OCaml with GABT, but it's not that important. Create just gives back a new key. You can see that. Oh, never mind. It's just details about the existential type variables, but we say they're not important. When a key is created, we get it as unique. We are the sole owners of the capsule, and in fact, creating the key is logically the same as creating the capsule. There is no physical representation of the capsule. Another thing to note is that this default annotation says that if we don't specify a mode for a key, then by default we treat it as portable and contented. This is the mode of shareable values. They are portable, so they can be shared between threads, and they're contented, so they can be captured by portable closures without them becoming non-portable. The data module encapsulates a value to be put inside a capsule. A capsule can contain multiple pieces of data, which are basically the capsule is made of the key and all the data protected by the key. The type of data is parameterized by the type of the contents and the variable that identifies the key that can give access to this data. Again, by default, this is portable and contented, so we can share freely data between threads. The key idea with capsules is that we want to gate all accesses to the values contained in the capsule by using this key. So we can't allow external references that point to values contained in the capsule. So when we create a piece of data protected by the capsule, we need to ensure that there are no aliases that point to this data. And we do that by creating data with a constructor function instead of accepting any value. And the constructor function must be local once and portable. So local ones are not that important. The important point is that the constructor is portable. So being portable, it cannot access its environment as mutable, because every value that is captured by a portable closure becomes contented. This constructor will be called with unit, will return the value to be stored inside the capsule, and will not be able to save this value in a reference, in a global reference, because it is portable. And then create returns a protected version of the value returned by the constructor. Then we need ways to access this data. The simplest is to destroy the capsule, and then we get back the values contained inside the capsule without protection. To destroy capsule, we first need to have full ownership of it. So we need to have a unique key, which is the same key that is protecting the data, and then we get back the values. The dot here means the default mode, so legacy mode. There are, of course, non-destructive ways to access the data contained in the capsule. So these are two functions, map and extract, that give write access to the contents. Since they give write access, they again require full ownership of the capsule, so a unique key. For example, map is taking a function that will be applied to the contents of the capsule, then the data, and then it returns the modified contents, or actually a new piece of data that is protected by the same capsule. So this, the contents of this data will be computed by applying this function to the contents of the input data. And then we also get back the same key we used to get write access to the capsule. So after we call map, we can still keep using the capsule with the same full ownership. Again, it is important that this function is portable because it gets access to the contents of the capsule. We don't want it to be able to leak the contents of the capsule because that will prevent us from guaranteeing the absence of data races. So we mark it as portable, and that's it. For extract, we have additional requirements. So the difference between map and extract is that extract doesn't return the value computed by the user function inside the same capsule, but it returns it as unprotected. So instead of a data B, it's just a B. And this gives the user some other ways to leak the contents of the data, which is to return it simply inside the B, or also to return a closure that has access to protected data. So we need to avoid this, and so we mark the return value of the user functions as portable and contented. So it is contented, so if it is a reference that is protected by the capsule, it will be inaccessible from the side because it will be contented. And it is portable, so if this return value is a closure, then it won't have access to the environment, to the mutable environment, so it won't have access to references that are protected by the capsule. Then we have shared versions of this map and extract. The shared versions require only partial ownership of the capsule, so the user function cannot modify the references, the mutable fields protected by the capsule. And to ensure that, we just mark the argument in the user function as portable and shared. So portable means that if the data we are storing inside the capsule is a closure, then the closure cannot provide a way to modify the environment. So we could imagine a closure that takes as input a value and writes it to a reference, and this will cannot be allowed because we are not able to keep track of this. So it could lead to erases. So we just disallow closures that access the environment. And then we mark the argument as shared. So if it is a reference or it is a struct which contains some references, then we can only read from those references. So the ownership here is partial, so multiple threads can invoke map shared at the same time. So we just we can only allow reading. In the extract shared is the same as before. We can't allow leaking the data through the return type, so we mark it as portable and contented. This is the whole implementation of the API. It's very simple. It involves a lot of magic. It's not scary at all. And of course, the modes here have to be chosen very carefully because it's very easy to invalidate the guarantee of data race freedom, since the implementation is not, of course, is not valid in the type system, and must be proved separately that it doesn't introduce any data races. So the API we saw now tracks ownership at the type at the type system level with these keys and their existential type variables. The problem we have now is that when we have a unique key, we have full ownership. If you want to send the unique key to another thread, we can do so when we spawn the thread. And the closure in the new thread can simply capture the key and we'll get it as unique. But then if we wanted to use the capsule also in the main thread, then both the closure and the main thread get used as aliased, which makes sense, just means that both threads have shared ownership of the capsule. But we don't have a way to transfer the full ownership from the main thread to the child, and then again from the child to the parent. So we cannot transfer full ownership more than once. And this doesn't allow us to implement channels or bidirectional communications in any way. And so we want to solve this problem. And we cannot do that statically, not in this framework at least. So what we do is to extend again the type system with another API that will expose a safe interface to the user and will be implemented in an unsafe way. This is the reader-writer lock API. Basically, it will a reader-writer lock is a lock that allows a single writer or multiple readers. This lock is specialized to protect a key, so not runtime data, but just the ownership of the capsule. And the lock will give the key uniquely to a single writer thread or aliased to multiple reader threads using these two functions, unique protector and share protector. So we can create a lock by giving the lock ownership of the capsule. So give it the unique key. Then we can get back the key for a limited amount of time using these two functions, unique protect and share protect. Unique protect takes a user function that will be given the unique key, and we return some value of type B. And also we return the key. So by asking the user function to return the key as unique, we are sure that the user function is not leaking it in any way, because if it does, then it has nothing to return here, because it must be unique, cannot be copied. And then, this unique protector will be implemented with a runtime lock. So just a runtime check that two threads don't call unique protect at the same time. If they do, one is put to sleep while the other executes. The return value here B, as in the capsule API, must be portable and contented to avoid the leaking data protected by the capsule. Then we have share protector, which does the same, but gives the user function an aliased version of the key. So here we are not saying that it is unique, so it is aliased. The key is also marked as local to ensure that the function doesn't leak it. Here we need to explicitly mark it as local because we don't have the guarantee that the key will not be leaked that we get from the fact that it must be returned here. And yeah, again, must be portable and contented the data, the return value. So combining the reader-writer lock and the capsule API, we can actually get shared data structures that are that have interior mutability, interior aliasing, and they can be sent back and forth. We can implement channels and so on. So here, for example, we are creating a key. We are creating some data that is protected by the same key. Then we create a lock that protects the key, and then we spawn two threads that execute the same function f. In this function, we are acquiring full ownership of the capsule, and then we are applying this update function to the contents of the capsule by using the key we get from the lock. The paper also contains an example of wrapping the hash table implementation of the OCaml standard library with this capsule API to get a concurrent hash table. And that doesn't require modifying the code of the hash table, except for adding some modal annotations. So we don't want to add modal annotations to existing sequential code, but here we're turning a sequential data structure into a concurrent data structure, so it is expected to be required to do that. So some example of annotation we need to add is that I define the method of the hash table. It doesn't modify its argument, so we mark as shared the hash table that we give to find. Okay, and then again a recap with the new uses we got out of the mods. Uniqueness now helps us keep track of the ownership of the capsules statically. Locality grants temporary read access in the share protect method of the read and write lock. Then affinity is not used directly, but is needed for the duality with uniqueness, so we can have closures that capture unique values. And finally, portability and contention for the same sharing exommutability discipline. So basically, up to now, we saw the user-facing part of the paper. Then the rest is the formalization and actually proving that the capsule API and the reader writer lock API do not break the data race freedom property. I go on now. I'm sure you're interested in this. So we have a Lambda in the name. So we start. Yeah?
In what measure does the programmer have to annotate the code with the modes and modalities, and how much is there an inference?
With the current, like the contents of the paper, there is no inference at all. But in Oxidizing OCaml, they have a pretty good inference. So the idea is that it can be extended to. Yeah, of course, it will be required for this of practical use because nobody wants to annotate the code. Okay, so the formalization basically starts with some calculus that will serve as a model of OCaml, concurrent OCaml with references. So we just start from the Lambda calculus, we extend it with references and threads. Also, this calculus has some nice features. For example, it distinguishes heap allocations and stack allocations. It has both atomic and non-atomic memory operations, and also has a borrowing construct, which I don't think we'll see, but just to say. The only thing I want to tell you about this calculus is the way it models data races, which is quite interesting. So just to recall, a data race is like happens when two threads access the same memory location, and one of the two accesses, at least one of the two accesses, is write, and the operations are not atomic. The calculus, the operation semantics of this calculus is defined such that when, like, if a data race is possible in a program, then one of the possible executions of this program leads to at least one thread being stuck. So if we can prove the progress property, so that a well-typed program doesn't get stuck, then we also prove the absence of data races. And this is the proof technique that will be used to prove the absence of data races. And so, to see it in more detail, this is how we model reads and writes in the operational semantics. So each memory location has a value and also a tag, which is Rn or WR. The tag tells us the number of threads that are currently accessing the location. So Rn means there are n threads currently reading the location. WR means there is currently one thread writing. Of course, other combination of like a number of readers and writers are not valid. And then in the operational semantics, we perform the reads and writes in two steps. In the first step, we update the tag, and in the second step, we actually perform the operation. So this is the rule for the first step of a load. We require that the memory location we are trying to read as RM type. If there is a data race, then it is possible for one thread to begin its first step and the other thread to begin its first step as well before the first thread ends the operation. So for example, if the first thread is reading and the second thread is writing, then after the first step of the first thread, the tag is R1. And then we try to execute the first step of the second thread, but it is expecting R0. Instead, it reads R1, so it gets stuck. And we have a stuck execution, which will be our marker that we have a data race. So going on from the calculus, we have a syntactic type system, or a syntactic formalization of the type system, which will be used mainly for presentation actually, because the proofs are done in a semantic version of the type system with a program logic. Maybe we'll talk about that as well. So the type system includes basic types, unit, boolean, integers, sums and products, the function types annotated with modes, modalities, which are written with this funny box, references and atomic references. An interesting thing is the way we keep track of uniqueness and aliasing. We do that with a context that doesn't only remember types and the modes, but also can be used to set a value as unused. So this basically means we cannot use the value in this value x, but we remember that we have bound it so that it shadows previous occurrences of x. This is an example of a typing rule that is not influenced by modes. So it's basically the rule for typing pairs. So it is the usual typing rule for products, but we need to propagate the mode. So we use the same mode to type the two sub-expressions. And also we need to split the context when typing the sub-expression to keep track of aliasing and mutability and uniqueness. The context is split with this context joining operator. This is the definition. Actually, I find it easier to read from right to left. So if we start in the context, we have an unused variable. Then when we split the context, we can put the unused variable in both of the two contexts. If we have it with a specific mode or a specific type of mode, we can choose to put it in the left or right context, and the other one will get an unused binding. But also, this is not like a linear type system, so we can also copy the variable. We can only do that if the variable is many. If it is once, we cannot copy. And when we copy, we get a binding in both the two contexts, but we get it as aliased. So if it was unique, after we copy, it becomes aliased. This is just an elegant way to keep track of these two modes. This is an example of a rule that actually has to deal with modes. This is the rule for typing lambdas. So to recall a closure, the way that a closure interacts with modes is that some bindings are inaccessible depending on the mode of the closure, and some bindings change their modes. So if the closure is portable, it cannot it sees its environment as contended. So if a variable is uncontended in the context, then it becomes contended, but the closure can still access it. But for example, if a closure is global, then it cannot access at all local variables in the context, because that will be unsound. It will lead to accessing a value outside of its lifetime. So we do that with this lock operator, which is applied to the context. It means that all the bindings left to the lock are modified according to this locality, affinity, and portability. And for example, this is the important case. a binding X which is protected by a lock or modified by a lock can be made unused if the mode of X is not compatible with the mode of the closure. So, for example, again, the X is local and the closure is global. Or it can be changed according to this fine expression with a join and a dagger, and we will not see the definition, but intuitively this means, for example, that a many closure transforms all its bindings, all the bindings in its environment to arrays. Okay, and this was some points about the syntactic type system. So actually, as I said, the proofs are conducted on a semantic presentation of the type system. The idea with a semantic type system is that first one defines a program logic. So you can think or triples, or actually in this case will be weakest preconditions. But you can think or triples if you don't know weakest preconditions. Which then lets us prove properties about the execution of programs. And one property in particular we are interested in is progress, as we said. So we want to prove that well-typed programs do not get stuck, so they do not have data races. And for that, we prove an adequacy theorem on the program logic, which means if you can prove a weakest precondition on an expression, so an arbitrary or triple on the expression, then it means that the expression doesn't get stuck. And once we have that result, we get that proving weakest preconditions is the same as proving the absence of data races. And then once we have the program logic, we define logical relations and semantic typing. So the idea is that each type will become a logical predicate, which holds on a given expression or value if the expression is of the type associated with the predicate. And the logical relation for expressions, so the predicate tells us if an expression is of a given type, is defined in terms of weakest preconditions. So if we can prove that an expression is of a given type, then we are also proving that that expression doesn't have data races because it doesn't get stuck. Then once we have this semantic version of the type system, we can use it to prove the soundness of the capsule API. The idea is that when we do all these proofs, so the adequacy proof, the proof that like the definition of the predicates for the various types, we do not rely on the precise definitions of the predicates, but just on a set of like coherency requirements or basically monotonicity requirements. And so we can extend the predicates, so add the new types and define the typing predicate for the new types without redoing all the proofs, which will be needed if we were using structural induction, the syntactic type system. So it is easy to define new types for the capsule API, give them a semantic interpretation, and improve the soundness with this extension without like doing additional work. Then why do we have the syntactic type system? The reason is that the semantic type system is quite hard to understand, so it is easier to present the syntactic typing rules. Also, the syntactic type rules can be made to be algorithmic, and so we can automatically check that programs are well typed, while checking the validity of a logical predicate on an expression is another problem, and usually has to be done by hand. And finally, we can extend the syntactic type system once we have proved the soundness of the extension with the capsule API and the reader writer lock API. We can simply extend the typing, the syntactic type system with the new types and the new rules, and we can just trust the proofs we did on the semantic type system. And so we get the best of both worlds. We get algorithmic typing that also works on unsafe programs that cannot usually be typed with a syntactic typing also. Okay, I think we can stop here. Unless you want to see the semantic typing rules, but it requires some stomach. Just no, this is the easy stuff. This is okay. This is the logical relation for expressions. So it requires some familiarity with iris, but the idea is that an expression E has type tau if it satisfies this weakest precondition. So after executing E, after executing E, we get a value that is of type tau according to the logical relation for predicates. And then we also need to keep track of the set of available references and the fact that we own the local values, so we own the memory, we have permission to reclaim the stack and so on. And then this is the logical some part of the easy part of the logical relation for values, which includes like some predicates for the simple values such as booleans. And this we are just checking that the value has the right shape. And then for products, for example, we need to check that the shape is correct, so we are actually V is actually a pair, and also that the two components of the pairs have the correct types. So the first component is of type tau1, and the second component is of type tau2. These are the modalities we know them. And then for function types. We need to prove that in all environments in which we can call the function, if we get a value of the correct type, an argument of the correct type, then the function call returns a value of the correct type, and there is some like keeping track of what is a valid environment that a function can be called in, and this depends on the mode. For example, a portable function cannot access its mutable environment, so it must be callable and valid to be called in all environments that have any references. But if a function is non-portable, then it can capture its mutable environment, so we can only call it in an environment where the mutable references are still valid. The mutable references that were alive when the closure was defined. And this basically is telling that the garbage collector doesn't collect stuff that we are relying on for the execution of this closure. But yeah, just because we wanted to see it.
Yes, online Bob says that this looks a lot like Egyptian text. And Alessandro Scala noted that there are some smiley faces, and
we can try to find them. If you have other questions in the meantime.
Yeah, in the unit there are a few smiley faces.